someone that makes me feel seasick. Oh, what a skill to have, oh, what a skill to have so many skills that make her distinctive.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Let's start out by talking about monosaccharide molecular structure. So as I mentioned before, monosaccharides are the most basic unit of carbohydrates. So they're the simplest sugar and they're often sweet to the taste. And so a key example of monosaccharides is glucose, and this is a molecule you're going to have to memorize for this course. And so in general, all important monosaccharides have first a chain of 3 to 6 carbons. And depending on the number of carbons they have different names. So when they have 3 carbons, they're called a triose. When they have 4 carbons, they are called a tetrose. For 5, which I'll write right here, it is a pentose. And finally for C6, this is hexose. So all of these prefixes is a common way to characterize different number of carbons, and this "ose," which is the suffix, is for saccharides or sugars. And then secondly, all important monosaccharides have one aldehyde or a ketone. So this is why it's really important to know your functional groups really well, because now that we're talking about biomolecules, they play a very important role. And so if a monosaccharide has an aldehyde, they are called aldoses. And remember, an aldehyde is when you have a carbonyl group, a C double bond O, and then an R group, but then a hydrogen attached to one of the carbons. And then if you have a ketone, you guessed it right, it's called a ketose. And in this case, you have the C double bond O, but then it's attached to 2 different R groups instead of a hydrogen. And the aldehydes, or the aldoses, are more common. And the position of the aldehyde or ketone is very important for when we name monosaccharides. Number 3, all other carbons are alcohols. And the key thing I wanted to mention here is that depending on where the OH groups are, we can also have D or L configurations. So let's look at this example right here with glucose. Let's make sure it has all 3 of these characteristics. First of all, it has a carbon chain of 1, 2, 3, 4, 5, 6. So it's a hexose. And since it has this C double bond OH group right here, it is considered an aldose. And all other carbons are alcohols, as in this carbon, this carbon, this carbon, this carbon, and this carbon all have an OH group, a hydroxyl group. So glucose is an aldose, which has 6 carbons, and all of these carbons have OH groups. Okay, so now let's look at this D-aldose family first off. And when we talk about D or L configurations, I wanted to let you know how you can differentiate between, for example, D-glyceraldehyde and L-glyceraldehyde. So it's called a D configuration if the OH groups is to the right of the last stereocenter. So as you can see, this is why learning about stereochemistry was really important, because now you have rules like this that involve being able to tell where the stereocenter is. And for L isomers, it's if the OH group is to the left of the last stereocenter. So in the case of the D-glyceraldehyde and L-glyceraldehyde, it only has one stereocenter, right? It's this carbon right here. So now looking at this stereocenter, if the OH group is to the right, like so, it's D. If it's to the left, it's L. It's as simple as that. But when you have more than one stereocenter, it's always based upon the last stereocenter. And I'll show you a little more of that in a second. So now let's practice naming some monosaccharides, and we can use all the different things that we learned in the previous slide. And so we have to always number the number of carbons, right? So in this case, I went from 1, 2, 3, 4, and 5. So always start at the top in terms of the numbering. So the one closer to the aldehyde or the ketone. And then we always have to name the number of carbons that are in the molecule, right? And so in this case, since we have 5 carbons, it's going to be a pentose. So I'm going to write that down as the suffix. So the second thing we talked about was whether something is an aldehyde or a ketone, right? So we have to figure that out too. So looking at this CHO group, what this actually looks like is, if this is the R group, that's this whole attachment, we have a C double bond O and then an H. So this is an aldehyde. So when you have an aldehyde, the prefix is going to be aldo. So this molecule is aldo pentose. Pretty straightforward, right? And so now we have to figure out whether it's a D or L configuration. And the rule that I told you is that you have to look at the last stereocenter. So in this case, the last stereocenter is this carbon number 4. So I'm going to put a star on it because carbon number 5 has 2 hydrogens attached in addition to the OH and this big group, and thus it's not a stereocenter. So now looking at carbon number 4, the OH group is to the left. So if it's to the left, remember, it's an L, right? So this is L-aldo pentose. Pretty straightforward as long as you remember the rules, and I think a really good way to just remember the L versus D configuration is that L is the left. And so now let's look at this guy. I numbered it 1, 2, 3, 4, 5, 6, and thus it's going to be a hexose. And now looking at this carbonyl group, we can see that this is a C double bond O, and then we have an R group, the CH2OH, as well as this other big R group, and thus it's a ketone. And when you have a ketone, the prefix is going to be keto, and thus this is going to be ketohexose. Really easy. And now we look at the last stereocenter, which is carbon number 5 in this case. Again, CH2OH, this carbon is not a stereocenter, and the OH is to the right. Now when the OH is to the right, it is D. So it's D-ketohexose. Now let's look at these two molecules. When you first look at it, they kind of look similar, right? That's because they actually have the same molecular formula. But we have to look closely in order to designate the names. So in this case, we have 6 carbons, and thus we know it's going to be a hexose. It also has an aldehyde group up here, so we know it's going to be aldohexose. But since the OH group on the last stereocenter is on the right, it's going to be D, aldohexose. But looking at this guy, since it has 6 carbons, again it will be hexose. And it has an aldehyde group, so it would also be aldohexose. But the final stereocenter has an OH group to the left, and thus it's L-aldohexose. So now you can see why it's really important to distinguish between L and D configurations, because these two molecules have the OH groups at different locations, but they have the same molecular formula. So one thing that I really wanted to emphasize was that there is no correlation of D versus L isomerism with plus or minus or R and S, where these things are what we talked about beforehand. Remember, R and S we use to label different stereocenters, and we also use plus and minus to talk about the direction in which plane polarized light is rotated. But in this case, this D and L configuration is solely for these biomolecules. And so you can't really correlate any of these together. So just because something is an L-aldopentose doesn't mean that it's plus or R or S. So just make sure you don't confuse these three different things together.
Bridget Jones.